Hi everyone, I'm Micaiah, and this is my report for Lab 5, Faraday's Law. The purpose of this lab was to observe the interactions between a falling magnet and an aluminum foil tube, as well as replicating the experiment in a computational model. The time that it took for the magnet to fall through the tube in real life was 1.672 seconds, but in the computational model it took 1.057 seconds. The physics principles involved in this lab were the Biot-Savart law, particularly with the magnetic field of a current-carrying wire; Faraday's law, which deals with the change in magnetic flux; Lenz's law, with the induced current due to the falling magnet; Newton's second law, F equals ma. So for the procedure, we downloaded Tesla meter and determined the magnetic north on the bar magnet. Then we held the aluminum tube vertically without touching any surfaces and dropped the magnet through the tube and recorded the time it took to enter and exit the tube, and repeated this procedure 5 times. Here's my trials. The average time that I took again was 1.672 seconds. So for the coding, first we added the geometry of the tube, as well as adding the magnetic moment of the bar magnet. Then we added 2 functions, one to determine the magnetic field of the bar magnet, and the other was used to find the magnetic flux through each ring due to the falling magnet. Then, for the next line, we calculated the current in the ring, and for steps 5 and 6, we found the typical B field at each ring. And then for step 7, we found the gravitational force on the magnet. Then we calculated the net force due to the gravitational force and magnetic force. And for the last step, we did an iterative process where we updated the position and velocity of the magnet. Here, you can click on this link and it'll take you to my code. This is what it looks like. And as I said again, the average time it took was 1.057 seconds in the model. So, as we saw with the falling magnet, counterclockwise is blue and clockwise is red because, due to our right-hand rules, the increase in change in flux is downwards, so the induced current must go counterclockwise. So, if we change the dynamics of the system and flip the magnet around, the magnet would still be slower than the computational model, but would be faster in real life. So, notice that the real life time is much slower than the computational model. The computational model is more accurate because it uses more rings and changes the value of mu. Since the magnetic field opposed the acceleration due to the force of gravity, you can see in the plot that the magnet's acceleration remained constant as it fell through the aluminum tube. So we'll end this presentation with some final questions. So if we got the resistivity of the conductor as close to 0, the induced current would become larger due to Ohm's law. As R decreases, I increases. What if the holes or slots were cut into the tube? So this would affect the ring's currents in our model because it would fall faster since there would be less magnetic force. Thank you so much for watching, and I will be back with more physics fun.